Welcome to today's Explainer. We're diving right into the incredible, completely invisible engine that's literally transforming how we explore the universe. When we think about astronomy, we usually picture these massive telescopes gazing up at the night sky, right? But the truth is, today, the absolute most powerful tool in an astronomer's toolkit isn't a glass lens or a giant mirror, it's artificial intelligence.
Here's our roadmap for this explainer. First, we'll look at the cosmic data deluge. Then, we'll see AI acting as the ultimate assistant, before meeting the autonomous observer. After that, we'll dive into how AI is actually evolving algorithms and wrap up with the human-AI collaboration.
All right, part one, the cosmic data deluge, which is creating a massive bottleneck for scientists.
Just try to imagine the sheer volume of data we're capturing right now. The soon-to-be-completed Vera Rubin Observatory down in Chile. It's going to take images so massive, you'd need 1,500 high-definition TVs just to view one of them in its entirety. Over 10 years, we expect it to generate 0.5 exabytes of data. To put that crazy number into perspective, that's equivalent to 50,000 libraries of Congress. Human beings simply cannot process that by eye. No way.
And this is exactly why AI has become absolutely crucial. To clear this bottleneck for cutting-edge instruments like the James Webb Space Telescope, deep learning models step in. They've accelerated data processing from what would literally be years of painstaking manual labor down to mere days. It's a total paradigm shift in how we process the cosmos.
What's really wild is that every major modern observatory isn't just a giant telescope anymore. They are massive data processing hubs utterly reliant on AI just to function. Take the Square Kilometer Array, or SKA. It's going to archive an astonishing 700 petabytes per year, using AI to detect pulsars in real time. Meanwhile, that Vera Rubin Observatory we just talked about, it'll use an AI-powered pipeline to ingest 20 terabytes a night and spit out alerts on unexpected cosmic changes within just 60 seconds.
Moving on to part two, AI is the ultimate assistant, making sense of all this data.
Now you might be wondering, is this all brand new? Well, actually, AI in astronomy didn't just appear yesterday. If we trace the history back to 1990, astronomers at the University of Arizona were already using early neural networks to study the shapes of galaxies. Over the decades, as the tech got more powerful, AI transitioned from, a neat little experiment into a completely foundational tool.
AI has proven incredibly successful at solving that classic needle in a haystack problem. For instance, by applying machine learning to the NEO-WISE infrared survey, a high school student actually built a model that uncovered 1.5 million previously unknown objects. Wow. In another project, a convolutional neural network classified 27 million galaxies with 97% accuracy. And NASA's TESS mission? They used an AI pipeline to validate 118 completely new exoplanets. It's just so good at finding hidden cosmic objects that humans frankly couldn't process.
This brings us to part three. Enter the autonomous observer, where AI starts taking the lead.
So instead of just finding what we explicitly ask it to find, AI is now out there trawling through massive archives and flagging completely unexpected anomalies at lightning speed. Take a pipeline called Anomaly Match. It recently processed 100 million image cutouts from the Hubble Legacy Archive in just 3 days. 3 days! It didn't just organize them either. It flagged bizarre outliers, which led to the discovery of 86 candidate gravitational lenses and 18 incredibly rare jellyfish galaxies. Those are galaxies whose gas is literally being stripped away as they speed through space. And now, we're actually seeing the prototype for a true AI astronomer. Meet Star Whisper. This is an autonomous AI agent powered by large language models. It autonomously plans nightly observations across a network of 10 telescopes, processes the images on the fly, and even triggers follow-up observations for things like exploding supernova. It essentially takes hours of manual telescope planning and crushes it down to mere seconds.
Which brings us to a fascinating, and frankly, kind of mind-bending frontier. Think about it. If AI can plan our telescope schedules and spot deep space anomalies, can we actually trust an artificial intelligence to write and evolve the complex cosmological algorithms we rely on to simulate the universe?
Let's explore that in part four, evolving algorithms with AI.
Enter MadEvolve. This is an ingenious system that acts sort of like a tireless digital apprentice. It takes our existing, human-written scientific algorithms, pokes and prods them, and fundamentally improves them. It works by combining the language understanding power of large language models with the survival of the fitness mechanics of evolutionary programming.
Now, because large language models can sometimes be a bit flaky with hard physics, we've all seen AI hallucinations, right? MadEvolve relies on a strict four-step loop to keep the AI honest. It doesn't just ask the AI to invent new physics out of thin air. Instead, it samples a parent algorithm, prompts the AI to mutate or modify the code, evaluates those changes against strict human-defined physics metrics, and then updates the population. It basically ensures the AI only keeps code changes that actually improve performance.
This AI evolution leads to absolute mind-blowing efficiency in how we model the cosmos. Get this, creating super-resolution dark matter simulations used to take 560 hours of processing time on a standard CPU. But by using an AI emulator, specifically a generative adversarial network, which is where you pit two neural networks against each other to improve accuracy, scientists dropped that processing time to just 36 minutes, and they generated 512 times more particles while doing it. That is a real game changer.
Finally, Part 5, the human-AI collaboration and the strict guardrails keeping it all safe.
Over at NASA, AI is practically everywhere at this point. The agency currently tracks over 600 specific use cases for AI. We're talking everything from prototype research tools to absolutely critical systems, like the autonomous navigation that lets the Perseverance rover safely drive itself for hundreds of meters on Mars. But, as you can imagine, high-consequence tools undergo incredibly rigorous testing before they are ever deployed.
As NASA's acting Chief Data and AI Officer, Kevin Murphy, reminds us, these powerful AI models are entirely dependent on quality data and human oversight. You know the old saying, garbage in, garbage out, right? Well, if you don't use the tools correctly or if you feed them bad data, you're going to get bad results. It's that simple.
Ultimately, the whole shebang comes down to accountability. AI doesn't make the final decisions. Scientists retain full responsibility for the outcomes. NASA enforces some absolute guardrails here. Humans are always in the loop for critical decisions. AI is strictly barred from executing unsafe actions, and there is a hard prohibition against using AI to create synthetic mission photos, like, say, faking a spacewalk, that could mislead the public. Trust is absolutely paramount.
So as we look to the stars, this human-AI partnership leaves us with one incredibly provocative question. As our telescopes get better and our datasets grow infinitely larger, what hidden cosmic truths will we discover next when we co-pilot our exploration with artificial intelligence? The next great astronomer might not be human at all, but rather a brilliant, seamless collaboration between human ingenuity and machine efficiency. Thanks for joining me on this explainer, and as always, keep looking up.